This is a video for MEI Core Pure Mathematics, Hyperbolic Functions 2, Inverse Hyperbolic Functions, 2.4, Integration using Hyperbolic Substitutions. Using a substitution can be a good way to integrate an expression. And if we think about this expression, the square root of x squared minus a squared, then this substitution, x equals a cos u, might be useful. If you think about putting a cos u in place of x, you'll end up with something that will look like this. You'll have a squared cos squared u minus a squared. And the important thing here is that the a will come out of the square root, leaving with something which is cos squared u minus 1. And we already know that cos squared u minus sin squared u is equal to 1. So this thing that's inside there will actually just become a root sin squared u, which is of course just a sin u. So you can see that this kind of substitution will give you a relatively simple outcome. Now, in a previous sequence of videos on trig substitutions, we've seen a similar technique, and if you haven't seen those yet or have forgotten about them, you may want to review that section on using trig substitutions. We're going to start by looking at using this kind of substitution in here. Now, in the previous slide, I talked about how using this kind of substitution could give you a factor to take out of the square root. And if I try something like x equals 3 cos u, then I would expect a factor of 9 to come out of the square root, and therefore it would be 3 times the square root of something. Let's have a look at the first derivative of that. Dx by du is going to be 3 sin u. And then if we plug those bits and pieces into the integral, so the integral of x squared minus 9 square rooted dx will be, well, I hope you can see that I'm going to get that 3 coming out, root cos squared u minus 1, and that's going to be times dx by du du. Dx by du we know is 3 sin u, and so this is going to become 3 times the integral of sin u, cos squared minus 1 is sin squared square rooted, times 3 sin u du. And so that gives me 9 times the integral of sin squared u du. Now, in order to do sin squared, we can't do it directly, but I've been given here an identity that I can use. So the double angle, cos of the double angle, is 2 sin squared u plus 1. So rearranging this, I'm going to be able to do a transformation on here to hopefully something that I can integrate more simply. And we'll have a look at that in a moment. There's a neater write-up of that. Here's the trial substitution and its derivative. And then we've done cos squared minus 1 is sin squared here. Dx by du is the 3 sin u, and then just tidy that up. So we're going to continue from this point on the next slide. So there we have it. We want to look at 9 integral of sin squared u, and I hinted that we were going to rewrite this. So sin squared u from that will be cos 2u minus 1, but it'll be a half of it. So I can put that into here to get that that is 9 over 2 times the integral of cos 2u minus 1 du. Integrate cosh 2u, we're going to get sinh 2u, but remember there's a 2 here, so we're actually going to get a half sinh 2u. So I'm going to get 9 over 2 times a half sinh 2u minus u plus a constant. Now I need a way to get back from here into something in terms of x, and the starting point we've got is that x was equal to 3 cosh u, which means that cosh u was equal to x over 3, and this also gives me that u is equal to r cosh x over 3. Now I've got u and I've got cosh u, but unfortunately I've got sinh 2u here. But if you look at this identity, I can rewrite sinh 2u in terms of cosh and sinh. That's just going to become 9 over 2 cosh u sinh u minus u plus c, and that's just, I've got a half of sinh 2u, so the 2 and the half cancel. And from here I know that cosh u is equal to x over 3, so that means that sinh u, which is the square root of cosh squared u minus 1, is going to be the square root of x squared over 9 minus 1. And we could actually do a little bit of tidying here, take the factor of 1/9 out of the square root, so that would be 1/3 the square root of x squared minus 9. I've now got all the bits that I need to convert this back into something in terms of x. I know that cosh u there is x over 3. I know that sinh u is a 1/3 root x squared minus 9. And I know that u is r cosh x over 3. And all of this is times 9 over 2, and I need to remember my constant. Now if we multiply that on through, I'm going to get x over 2 times root x squared minus 9 minus 9 over 2 r cosh x over 3 plus a constant. And that's the neater version of the write-up of that. So here you can see we've used this identity to get us down to this version here. We've then integrated that and then used this identity to get this bit out. And then we've used all of these things here. So cosh u is x over 3, rearranging to get sinh u in terms of x and u in terms of x, and plugging all of that in, we get down to here. So using the substitution gives me something that I still have to do work on, a bit of double angle formula stuff here, and then have to do quite a lot of work. This little red box here represents quite a lot of work to get back to something in terms of x. So it's not all plain sailing. There is work to do to get this to come out properly. So the summary then for hyperbolic substitutions, we'd use something of the form a cosh u if we've got something involving the square root of x squared minus a squared, and something like a sinh u in expressions involving the square root of a squared plus x squared. Important things to notice: you may need a further technique to be applied, and we use the double angle formula in our example. And transforming back to the original variable may take some care, so you may need to do a bit of work to make sure that that works out properly. That was the final video in the sequence Hyperbolic Functions 2, Inverse Hyperbolic Functions.